Are you tired of entertainment being single player and screen bound? Well, do we have a solution for you? Here you go, Bing.
Whoa.
Come on, Vivian.
Where are we going?
We're going to Team C5 HoEM Run Derby. Hello, my name's Aiden, and I worked with Bing and Vivian to create HoEM Run Derby, which is our project for our senior year capstone as electrical and computer engineers at Carnegie Mellon. So we recognized that entertainment was screen-bound and single-player, and there's some lost art in the arcade experience that our parents once had. So we identified that the arcade experience was socially immersive and engaging, and we wanted to fuse the physical, nostalgic feel that these games had with the modern control that we can achieve with electronics. Before developing our full solution, we identified some requirements. We wanted the game to be two-player and portable. Portable is for practical reasons. Ideally, you can set this game up quickly and put it away, and also for us in demoing, we wanted this. And we also talked a little bit about the gantry motion and coupling. Now, this is getting into our solution a little bit, but we wanted our game to be very functional, and we wanted it to be very fast. We were doing some case studies on simple arcade games like Whack-A-Mole, and we were trying to figure out what made such a simple game so fun. And we recognized it was the physical experience as well as the response that you get, the quick response. It feels snappy, and it's just something that you want to continue to do. Of course, we also wanted our game to be error-free, because an error-prone game is not a fun one. Here's the solution we came up with. So on the left side, you can see our game board, and then the right is the bat. These separate as two subsystems, and the pitcher plays on the left side of the game board, and of course the batter is holding the bat on the other side. On the board, we see a scoreboard, and this holds a 7-segment LCD display. And there's also an acrylic top surface that's embedded in this plywood frame. And we chose this acrylic surface because it's thin and also magnetically permeable and low friction. So it enables us to carry this magnet on a gantry below the surface, and that will couple with the steel ball on top of the surface and roll cleanly. In the back, we see 3D printed pockets. Now, these pockets were all designed to embed brake beam sensors in them, and this allows us to detect a unique scoring outcome for all these pockets. So, for example, if you hit it in the leftmost pocket, that will be a double, but if you hit it in that back wide pocket, that's going to be registered as a home run, and the scoreboard will be updated accordingly. On the bottom, you can also see some funneling, and this enables the ball to drop through these pockets and return back to that pickup spot, the cutout protrusion, where the balls are then taken and placed back on the top of the board after one game cycle. On the right, our bat system is comprised of an ESP32 microcontroller that's powered by a lithium polymer battery, and also there is an inertial measurement unit, also known as an IMU, and this detects rotational velocity, which allows us to sense when a swing is swung and communicate that wirelessly back to the microcontroller on the game board. We also have a switch to select the threshold for this velocity. So if somebody's less physically able to swing the bat hard, we can still enable them to play by lowering the threshold at which the swing is detected. I'm going to walk through a demo of our project from a couple different views, starting with this side profile. Vivian's standing on the left side as the pitcher. She can select from 4 different pitch types, and this will vary how the ball is translated during the pitch. She could also vary the speed and then when to actually trigger the pitch with the pitch now button. I'm on the right hand side as the batter, and when I see the ball coming towards me, I'm going to swing my physical bat, which will trigger the servo on the board to flip and hopefully drop the ball into one of the pockets. If you pay attention closely to the scoreboard, you can see there's already one runner on first base, but after I hit another single, this causes the second runner to advance and then another runner to go to first base, leaving 2 people on. And I believe here I fake a home run, which results in all the bases being cleared and 3 runs being batted in. Now I'm going to show you a couple different angles.
I'm going to select a start-stop pitch, and then pitch now, and then swing. There you go, and then we got a triple, and if you can see the scoreboard, we should have somebody on third.
Here you can see another pitch type, which we call a ramp.
And then this W. There you go. Single. Runner on first. Good. So I'm going to select fastball. Pitch now. And let's see. Oh. That should get routed to
Good
an out.
fielding, good fielding.
There we go. 2 outs.
Good magnet.
This one's tricky.
And here's a block diagram going over that communication and control flow. We can see there's buttons that the pitcher can control the pitch and also reset the game. There's the sensors that we talked about to detect the scoring, and that gets sent all to this central game controller, which is also an ESP32. This controls the game state, and it updates the outputs accordingly, such as the LCD display. And the controller also communicates with the gantry controller, which is a separate ESP32 that runs a fluid NC CNC control package similar to what a 3D printer would run. The bat has its ESP32 and communicates with the ESP on the game board over this ESP Now protocol, and the game board controller communicates to the servo over a GPIO pin. Now here are some of our results put into a table. The swing latency we measured was from the time the bat was swung to the time that the flipper was actuated on the game board. Now we were going for 100 milliseconds because that was the threshold at which humans can perceive lag. We got very close with 150 milliseconds, and we actually deemed this satisfactory despite not being our original target. Coupling was satisfactory, however decoupling was not. Now this measures the frequency that the ball can stay on top of the magnet below the surface. So this, in other words, is like slippage. And when the ball is being pitched, we don't want the ball to slip off the magnet at all, but we want the ball to slip off at the end so that the flipper can cleanly hit it off of it into pockets. We did not get decoupling done because the mechanical complexity for the system we proposed to decouple the ball was very high in the limited amount of time that we had left. The gantry motion was very easy to repeat thanks to the robust control software and hardware. Gantry speed, while we only got to 250 millimeters a second, we also deemed that this was satisfactory. We thought that the ball was traveling very fast and it made our game feel skill-based. And fortunately, we were able to achieve the high scoring accuracy that we sought after. This project was very complex. Some would say we were swinging for the fences. Strict project management was key to our success, and also probably some of our downfall. We held weekly meetings trying to map out roadblocks and also areas where we can help each other. We also used this Gantt chart, as you see on the left, to delegate tasks and set deadlines. We broke down the game into 3 systems: the bat subsystem, which Bing took over, the pitch subsystem, which I took over, and then the game board, which kind of encapsulates all these tasks that Vivian took over. One thing I think we could have done better was leave more time for integration and testing. And to do this, we probably would have reduced the scope of the rest of our game. And here's a little montage of our development. On behalf of my team, we're very grateful for TechSpark and 88 as a whole for helping make this happen.